start in about 5 minutes, so you can still talk, and then in 5 minutes, JC will give a talk on Ensemble Learning and the Netflix competition, and then we'll open it up for discussion, and then I'll end the session hopefully within an hour 10 minutes with a small introduction about bootstrapping, so like a small statistical concept. We have a guest here who wants to tape the session. So if you don't want to be taped, let him know, and he will avoid you.
Yeah. So, if I could have everybody's attention. How many of you are familiar with the Netflix machine learning competition? Okay, good. So, as you know, what they want to do is see if anybody can improve on their, I think it's called Cinepred or Cineprix, method that they use for predicting what movies users want to watch, basically, based off their past viewing history. And the Netflix competition was held, I think, in 2009, and the reward was $1 million for who could best predict a set of user ratings from previous ratings. And the goal, basically, for Netflix, as far as they're concerned, is to maximize continued subscription to their service, to improve the user experience of their service, to get a competitive edge, basically, against other services like Hulu, etc. So, in the competition, competitors were given a data frame that looks something like this, where they have a date, a user, a movie, and a rating. And they had to use this to try and predict, basically, another set of identical data, but without the rating. So, the challenge is, how do we go from previous ratings to new ratings? Is everybody familiar with k-means clustering or k-nearest neighbors? I think some other popular techniques include factorization or just solving simple linear models. In general, people use the following techniques. So, factorization, SVD, what else do they use? Linear models. They also use a number of different clustering methods that you may be familiar with. K-nearest network, or K-nearest neighbors. What else? SVM. Support vector machines. They used neural networks. And they used restricted Boltzmann machines. Are there any of these that anybody doesn't know? Nearest neighbors, support vector machines, neural networks, and restricted Boltzmann machines. This one is a little less popular, but it's essentially a neural network that predicts a distribution. So the results from using these methods on this type of data, you might produce a prediction accuracy. So for each model, you'll have an associated accuracy. So for each individual type of model, you might find maybe 80% accuracy, 90% accuracy, 40% accuracy, maybe 30% accuracy. If I were to tell you that this is the result of your models, which one would you pick? Or how would you proceed? Anybody? You would pick the highest accuracy model, right? A lot of people, when they approach a modeling problem, they'll try multiple different methods of modeling an individual problem and just pick the best one. But what if we could take all of the models and combine not the intuition, but the results of all of them together so that you get more of their advantages and fewer of their weaknesses? If you look at these different modeling techniques, you'll notice that a lot of these have different assumptions. they require different shapes in their data, or they perform best when their data adheres to certain assumptions. But what if we could take these individual models and combine them in such a way that the modeling techniques are used on data for which they fit best? Basically, I'm talking about a method of ensemble learning. So in the Netflix competition, the top performing modeling techniques all involved ensemble methods. So the most popular one was stacking. And I don't know how many people are familiar with stacking in general, but it's a very, very simplistic technique. As a statistician, you look at a set of models like this and you go, okay, the first thing I want to try is a linear model. And that's exactly what it is. It's simply take the sum of all of your model results and weight them, basically forming a system of linear equations that you solve for a constant, and fit your model results to your data as best as possible. This is actually used in the medical industry for prediction of things like cancer survival rates, etc. And it's been shown that combining models in such a way often can improve the results of your predictions beyond the best prediction method. Sorry, this is the best one. So beyond the best prediction rate of your best model. And the intuition of this is fairly simple. If you fit a meta model, a model combining models correctly, you should perform at least as best as your best model. Basically, if you have a model that performs this well, and these other models do not contribute to your accuracy when combined, you should null them and just always pick your best model. However, if they do provide some benefit to your prediction accuracy, you will see improvements. So this is a pretty simplistic method of combination. It's probably the most simplistic you could imagine. But what if we used another related technique called blending? So there's the two people that tied for first in the Netflix machine learning competition both used a method of blending. The first, the absolute top winner, Belcour's pragmatic chaos, used actually a blend of blends. They blended models together and then blended their blended models together in a very complex hierarchy based off years of experience with Netflix type data. In fact, the people that developed Belcour's pragmatic chaos developed a pre-processing technique for dealing with movie ratings and users, that kind of data, to remove global level patterns from your data before trying to model individual patterns. And that method is so powerful that every single qualifying team for the Netflix competition actually used that pre-processing step. So they know their stuff. They were able to take their intuition, their understanding of the data, and produce very good models. Now the second team, the team that tied them for first, but who were 20 minutes slower and thus came in second place, used a method of blending that is so simple that you might even have trouble believing it. Their method of blending simply used a function of input data, f of j for all j meta features. Basically, taking user data and transforming it into meta features about the data. Features about individual points of your data. So meta features, examples of meta features might be whether or not that user watched more than X movies in a particular day, whether or not what the log n of the total number of movies that user has ever watched is, or the log n of the total number of movies rated, or how often that movie has been rated. Another meta feature might be the maximum correlation between two individual movies' ratings. So this function is used to transform their data into meta features, features about your features, basically. And what they did is they said, let's combine our model results for each meta feature and for each individual model. Let's weight them individually. So V of Ji will take our meta features and just scale them appropriately. So basically, this is your individual model prediction. This is your meta feature, which is modified by a term. And you just use this is again a system of linear equations, by the way. So you can simply just solve this on a cluster, you can solve it massively parallel, however you want to solve it. But once you get these coefficients, you can weight your individual model that you found based off features of the data in that local region in the solution space. What that lets you do is combine your models in such a way that your prediction accuracy is in general improved over even your best individual model. So despite the simplicity, the apparent simplicity of their meta model, they were able to tie tie accuracy with a very highly complex model based off years of experience with just that data, which is very impressive. Now, the great thing about having a linear model as your meta model is that you can take your prediction results and go in the opposite direction and say, what is it about this particular user that makes a rating easily predicted with an individual model? You can understand more about what it is that your users want and what individual classes of users want or need from your service. It lets you understand more about how you should operate potentially as a business, which is fantastic. And the great thing is, if you're doing this kind of analysis in the first place, chances are, if you're doing your analysis responsibly, you already have these models. You're already doing this analysis and comparing your models with each other. If you're not, you should be. So you have this information available to you. You might as well, rather than waste this effort, try and combine it so that you can get more of the benefits of all your models and fewer of their weaknesses.
Is it always like that? Like, anytime you combine models, are you always like amplifying the advantages?
No. In many cases, a model as simplistic as this, and even sometimes a model like this, won't necessarily improve the results. But it would be a waste of the effort constructing these models if you didn't try and combine them to see if it could make an effect. And in fact, the success of a model like this is highly dependent on your understanding of the meta features. So you need to understand what meta features are important, or have some kind of intuition about your results. And it's also very important that your results are labeled. This is ultimately a supervised technique. So if you don't have the results that you're trying to predict, you can't do something like this. This is not a data mining process. But that is a good question. Does anybody else have any questions? Please ask and talk. Yeah.
It seems like the second method you mentioned, as opposed to the winning method, came out 20 minutes slower.
20 minutes slower, that's right.
So this seems simpler. Why did it take longer?
Why did it take longer? It's possible that although the winning method was more complex, that ultimately computationally it was simpler. Solving a set of linear equations like this can sometimes be prohibitively expensive if you don't have the hardware. It's a trivially parallelizable problem, but if you don't have the hardware to solve it, you're kind of screwed. But even though it's slower, that doesn't necessarily mean that you can't take a model like this, a very simplistic approach to combining combining models, and use the intuition that you earn from this to create a more complex, more accurate, and faster model, such as Belcour's pragmatic chaos. Any other questions? Please, discuss what's up.
How much data did they use?
They were given a total of 500,000 users, 17,000 movies, for a total of 1 million user movie rating combinations, which is quite a bit. And their test data was substantially smaller, the data that they had to predict.
The other aspect in using an ensemble is even if you get those ratings on that specific set, when you walk out of that sample set, the one that scored lower would, the feature set of that would be different, so it would necessarily score higher,
Yeah.
and the higher one would be scored, so you get a sort of like an averaging for that.
You have to be very, it's true. And you have to be very careful when training your meta model too. The process has to be very controlled because fitting so many models, and especially a meta model, is tricky business. You run the risk of overfitting with very simple mistakes. And the way that the ensemble, the team that did actually use this method, performed their fitting was they had their training data, they split it up into a probe set, and then the remainder of the training data. They fit every model once to just the training data minus the probe, and then fit every same modeling technique against the both combined. They used the first set, which was without the probe data, to predict the probe data and then fit their meta model on that, the results of those predictions. And then they used the coefficients that they learned from this set to combine the models predicted against the whole. It's complex, but it avoids the problem of overfitting. And they used cross-validation. I believe they fit 10 times, just 10-fold cross-validation during this process, and chose the best.
What was the question?
I don't remember.
Seems like a small feature set, and Netflix
It
has
is.
access to far more data than this. Is there a reason why they limited it?
I believe they were given access to some extra features, and then a lot of the users themselves, not the users, but the competitors themselves, computed further meta features of the data, just to try and understand or split the data into pieces based off its local features.
And was it pure derived metadata, or did they bring in like the category genre of the film?
I'm not sure.
Okay.
In the end, using this technique, they combined over 120 models using 29 different feature sets, and unfortunately, I can't remember all of them. Otherwise, I could have answered that question. But you can consult their paper, which is available publicly, and it's a very good paper. I do recommend it, as well as Belcour's Pragmatic Chaos. And their papers in general are actually good.
But more features don't necessarily mean a better model either. Sometimes
That's true.
Less is a lot more.
Less is a lot more, yeah. They did do a training phase, learning which meta features provided the most information, and they cut them out, cut features out of their model that did not perform well. They did a few correlation methods to try and find out which ones perform the best. I believe they also used a few methods of punishing complex models, overly complex models. You can find more details about exactly what they did in the paper. You had a question?
What's the name of the paper they wrote? How can we?
So the team is the Ensemble, and I believe the paper was called Feature-Weighted Linear Stacking. Feature-Weighted Linear Stacking. Just in case anybody decides to write that down later.
You talked about the probe data earlier.
Yeah, they just call it probe data.
Okay, so was there something special about it, or is this like a random sample?
Randomly selected. So they were using a technique called cross-validation, where you ran.
Louder. We can't hear you.
Oh, sorry. Yeah, they were using a technique called cross-validation, where they take a sample of their data, put it out of bag, test against bag data, and then predict the out of sample data. And basically, what that prevents you from doing is overfitting. So, if you find that your predictions are bad, you know that your model has been overfitted or something about it is incorrect.
But in the real world, like, you probably want your model to fit samples that are not in your data, right?
Exactly.
So does it
You,
really
you
help?
kind of simulate that by assuming that the data set you have is representative of the population,
Okay.
and then you treat your data set as the population and take a sample of that randomly, and then treat this as what you're training against, and then treat the set that you took out as invisible hidden data that you test against later. So kind of simulate the process of, yeah.
Were they not allowed to take the name of the movie
And look it up and.
yeah, exactly.
I think they probably could have, yeah. So that might have been meta features that they.
Why didn't they do that?
They might have.
You write some code, go to IMDb and come up with 100 attributes and then off you go to the races.
Yes. So I believe actually that people did mention clustering movies based on similarity, and I bet that's how they did it. They also may have clustered them based on the similarity of ratings they achieved. I'm not sure.
Weren't you also saying that they had information about like the actors that were in the movie?
I think so, yeah. So
Then they had to have done it. They had to have created more attributes. And IMDb is available to the public, and you could write
Sure.
code to essentially go through all 17,000 movies and take out a couple of dozen attributes that you might think would be predictive and then add it to your database.
for sure.
Did they try any AI?
Yes. So some of the models that they tested, they combined 120, did involve neural networks.
Where I come from, neural networks is kind of like a hardware thing. What kind of AI were they using?
I don't have details about their neural network models, but I imagine they use probably fairly typical ones for classification, because ultimately the rating is out of 5. You could treat it as a class.
Right. But this is, in terms of the objective, is not different from some of the efforts of trying to predict box office.
Sure. Yeah.
It's the same process, just with a different objective function.
Mm-hmm. The nice thing here is you have user data as well, volunteered user data,
Right.
and a lot of it.
Right. It's really interesting that they could come up with things that were that predictive. What kind of parse words were they looking at the end?
So in the competition, you were disqualified if you didn't achieve higher than 91% prediction accuracy, I believe. So if you did,
With our scores, how they measure that.
so I think they measured prediction accuracy just by correct classification. I think they also looked at recall and precision to avoid biases in your data, like imbalanced sets of classes, for example.
Right.
If that was your concern.
Yeah. It sounds like the probe data was essentially a different way of talking about the data set.
It's
Dividing
basically
into
cross-validation.
Yeah.
But they talked about it using different terms, I think, just to clarify that there were multiple steps involved.
Right.
Because it starts to get confused if you read the paper top to bottom when they start talking about this sample and that sample, and it's easier just to read if it's labeled differently.
Did they try non-linear blending?
Belcore, I believe, did use nonlinear blending. That's another paper that I would recommend.
That'd be really interesting.
Belcore's pragmatic chaos.
Pragmatic chaos?
I don't remember what the name of the paper is, unfortunately, but you should be able to find it fairly easily with a search term like that.
Pragmatic chaos.
Chaos, I think, because of how complex the model ended up being.
Or it could be recent history in Europe.
Yeah, who knows?
Were the teams from all over the world?
I think everybody was allowed to participate. I don't know if you could qualify for the $1 million prize if you were outside of North America.
And they were all data scientists.
I think it was a collection of scientists from different areas, but it was a pretty popular competition a couple years ago. I think they're going to hold more, so if you're interested, I would recommend participating.
So in a way, though, Netflix is the real winner because they get all
They
this,
just win, yeah.
like computational power, right?
And it's $1 million. That's crazy.
Yeah,
How much
that's like
could you sell
change,
out to
right?
Amazon?
Yeah.
The winner to write their own code, or did they use readily available
I think they used.
tools? That they use the cloud?
I can't remember a tool you mentioned.
Have their own hardware.
I can't remember a tool you mentioned.
They had their own hardware. The winning team, they had his own hardware. They did it in the university, so they had access to very like good machine. There was a card like a couple months ago, so I don't remember very detail of it, but I know they use the machines in university.
Did they write their own code from scratch, or did they just use tools?
I imagine they probably used machine learning tools because they're just such a rich set of available tools for machine learning. I can't see why they would write something from scratch.
The reason they would do that is because higher the level of abstraction, the less efficient it is.
True. Yes.
And if you really want to speed it up, which is part of the criteria for winning.
Yes.
the
For
more-
breaking ties.
Right, but still, in the real world, you want to get an answer in this lifetime.
Yeah.
And there comes a point when you have to start writing your own code, because otherwise you're going to be waiting until there's no more use to the information.
Yeah. I'm not sure about the winning team, but these guys, they're just solving a system of linear equations. So what they could do there is very easily just call on any BLAS implementation, like high performance one.
Yeah.
And something like this is fairly trivial to whip up in any C-BLAS implementation that you could get your hands on.
And if they wrote their own processor, it's very possible that they wrote a lot about their models themselves.
Right.
A lot of these are theoretically interesting but simple in terms of their implementation. A lot of them boil down to linear algebra.
Do you worry that this experiment was using things that were too simple to be extensible either academically or operationally?
In the sense that you think the models they generated wouldn't be easily, or at least the methodology wouldn't be easily transferable to something else.
Not usefully transferable. For example, Thomas Powers. I've got a brand new car that I can drive for an hour without put on the brake or the throttle, and that's a pretty interesting experience. And that's going to be a transforming industry coming up over the next 5 years.
Yeah.
There's going to be enormous amounts of predictive analytics going to have to be done with that. And there's going to be a ton of data that's going to be really, really accurate.
Yes.
And I think that most of the people doing that now have gone beyond linear approaches. Most of it's already in the AI.
I believe you're correct. However, this is not merely a set of linear equations.
I agree with you. I understand.
Okay.
I'm not.
All right.
I'm trying to understand the applicability of the techniques here to actionable challenges in the real world today.
So in the paper about the ensemble,
Right.
you'll find links and references to other industries that have used stacking or blending.
Right.
This is closer to blending.
Yeah.
In various industries with great success.
Yep.
So you don't have to take my word for it that it works elsewhere.
No,
The question is whether or not it's the best approach, and there certainly may be better approaches depending on the type of information.
Supporting your point, most autopilots for jets use this exact same approach.
The stacking method. Yeah. That's very
Because
cool.
because it's really fast.
Yeah.
You know, it's really fast.
Mm-hmm.
And in the world of autopilots and jets, you're
Deadlines are the king.
Yeah, but
basically.
we're talking about 1,000 recalculations a second. And in order to do that, you've got to have simple analytics.
You have to have simple and fast for sure. Whenever you're dealing with a safety-critical real-time system, deadlines are king. Everything else falls to the wayside.
And autonomous cars, we have the same problem. These are really big.
Yeah, I do worry a little bit about autonomous cars because of the inherent complexity, and the fact that I find it difficult to believe that they would work well on a truly safe real-time safety-critical system.
The challenge with autonomous cars is that they're coming whether we like it or not.
Mm-hmm.
They're being tested on the roads here in Ontario as well as California, Nevada. It's happening.
Yeah, I have confidence that people will make them safe. The thing I don't have confidence in is their ability to make them secure.
Great point. Great point. Cyber risk is huge.
It's massive, yeah. People have already used fridges for, like smart fridges for DDoSing people, so it's really just...
The technology exists right now to put an app in your phone. You can go around the coast of a mall and play with people's Instagrams.
Yeah. I think you can still collect credit card numbers by walking around a mall with the scanner because of the near-field chips in credit cards, which is pretty fun.
I'm sorry you said that.
Yeah.
You're doing really important stuff.
Thank you.
Really important stuff.
I had a question about the intuition behind feature engineering. So
Okay.
I get what you presented with stacking and blending,
Yes.
and that's awesome stuff.
Very.
When you're starting from scratch, what would you advise as a process or reading material for that intuition of what's the process of looking at a set of features to start that process of engineering them, creating these meta features?
So for reading material, I can probably send out an email with some suggestions. As for approaching a new set of data that you haven't seen before, plotting visualization for sure. Systemic level statistics are great. And go simple. Don't try and make it complicated at first. Try and understand your system with the simplest techniques that you can at the beginning. Just linear models, simple prediction, see what happens with that. And you'll quickly get an idea of whether or not that approach is viable, maybe some systemic level things in your system. If you're looking at a time series, just do the basics. ARIMA is fantastic, and it's surprisingly robust, even in multivariate systems. Actually, one of the problems with more complex modeling methods on things like time series is that for things like, as an example, VARIMA, which looks at multiple time series and the correlation between them, is that you're estimating so many coefficients that the error that you gather from each individual coefficient can sometimes ruin the prediction that you get. It's depending on the error of so many different coefficients that even an ARIMA model can outperform a VARIMA model on a complex data set. So you must be very careful when using complicated modeling techniques. Thanks. Okay.
Let's take a 5-minute break and then I'll wrap it up with another tidbit of statistics.
Sure.
Right.
Okay.
Thank you.